It's finally time for us to start talking about the major concept in this class in Calculus 1, which is called differential calculus. And that is something called the derivative. To give you a little bit of historical context, the big questions that drove the development of calculus in the 1600s, there were really two questions that people wanted to find answers to. The first is called the tangent problem, and that consists of this desire to figure out how we find the exact slope and equation of the tangent line to a curve at a single point. We'll review what a tangent line is, but the one characteristic of a tangent line is that it goes through a single point. And to find slope, we need 2 points, right? It's change in y over change in x. At a single point, there is no change in y and there is no change in x. So this will give us a slope of 0 over 0. And so this was a difficult question for people to try to answer. The second question that drove the development of calculus, differential calculus at least, was called the velocity problem. That is a similar, related problem. And this is kind of wondering how we find the exact velocity of an object at a single instant in time. Or in other words, the instantaneous velocity. We're going to answer both of these questions. But you can see in the velocity problem, the problem is really similar to the tangent line problem. Right? Just as a reminder, velocity is change in distance over change in time. And at a single point in time, if you just take a snapshot of yourself at one point in time, you're not moving any distance and there's no time moving. So again, this will be 0 over 0. But of course, our experience of the world is at any point in time, everything has some kind of movement. So these questions we will answer in a very short amount of time compared to the amount of time it took for people to actually answer these questions. There were two people who developed calculus around the same time, within a year or two of each other. The first is Isaac Newton, and the second is Gottfried Leibniz. And they both kind of, I think, accused the other of stealing their ideas, but in fact, they just independently sort of solved these around the same time. So in general, differential calculus, again, which is what we're going to be studying in Calculus 1. Integral calculus is another branch that is typically studied in what you call Calculus 2. We're going to study slopes, or more generally, rates of change of functions. So I know we know what slope is, but that's just for lines. So we're going to talk about slopes of curvy things, things that have different slopes at different places, and then extend this idea to discuss more like rates of change of functions that maybe model a certain situation. So this is the first time that maybe in a math class that you get to have this dynamic approach to using mathematics to describe things that are changing over time. Right before this, in your other math classes, it's more of a static approach. Like you plug in an X value, you get a Y value out, and it's just, nothing, you don't consider how things are changing with respect to another. So this is the main thing that we're going to be discussing for a while. So let's get started. So this is the beginning of chapter 2, which is all about an introduction into what is called the derivative. And this first section, section 2.1, is about the derivative in the context of a graphical interpretation. In other words, slope. Okay, so 2.1 is called the derivative and the slope of a graph. So let's just take some time to make sure that we are all on kind of the same page about what a tangent line is and what a secant line is. Okay, a tangent line, like I mentioned before, is a line that goes through one point to a curve. In Latin, this tangent comes from the root word tangens, I don't know how you'd say that with in like actually in Latin, and this means touching. So that's where the word tangent comes from. A lot of math words are based in Latin. So tangent lines, if we look, for example, below here at this circle, if we want to find the tangent line to this circle, say at this point right here that I've indicated, that might look something like this. Okay, so it goes through that point, but it just kind of touches the curve in kind of like just very gently at that point and then keeps on going. In the middle, we have maybe an upside down parabola. Okay, so if we wanted to find maybe the tangent line over here, maybe take a sec, pause this video and see if you can sketch in what the tangent line to this curve might look like at the point that we have here. Right, and I hope yours looks something like this. Okay, it goes through that point and then just kind of, hugs it, touches it just the right way, and then it keeps on going. It just touches it very gently at that single point and then continues on its path. Okay, at different places, we would have different tangent lines. So if we have another point over here, come on, let me have another point. Okay, well, over on the left side a little bit. There we go, this orange point here. I'm going to take a sec to sketch in what this tangent line might look like at this point. And I hope maybe yours looks something similar to mine here. This would be the line that goes through that point and has just the right kind of slope there. This last example here, maybe kind of a flattened parabola if we wanted to find the tangent line right at this point right on the bottom there. This one might look something like this. Right, almost like a horizontal line would be the tangent line to that curve at that point. Okay, I'm contrasting this with a secant line. So secant in Latin, this means cutting. So this root secant comes from the Latin word secans, which means cutting. So a secant line is going to go through the curve at more than one point. So if we have a circle and we want to find the secant line between these 2 points, it's just the line that connects them together, right? So here's the secant line between those 2 points. This upside down parabola, if we want to find the secant line that goes through, for example, these 2 points here, it might look like this. And just the line that connects those two together. And here on our last curve here, say we want the secant line that goes through these 2 points. Here we've got one that goes like that. Okay, so secant lines and tangent lines could have positive slope, go up from left to right. They could have negative slope, go down from left to right. They could also be flat. They could have zero slope, just be a horizontal line. We're going to focus on tangent lines, but they are intimately related to secant lines, as we'll see. Just to summarize kind of the idea of what a tangent line is for us, there are mainly 2 things that we need in order for a line to be considered a tangent line. So a tangent line at a point needs 2 things. The first thing is that it has to go through the point, right? It has to actually go through the point that you're finding the tangent line at. That should make sense. So it has to go through the point. But that's not enough. It has to also have the right kind of slope. Like it has to have the right direction. It has to, kind of just touch the curve very gently at that point and then keep on going. It doesn't cut through the curve in a really abrasive way. Like if we were finding a tangent line at this point up here on this circle on the right, this wouldn't be tangent to the curve. It's cutting through it very violently. Like it's not very gentle, right? So the second thing that we need, this is what we need to spend a little bit of time kind of thinking more deeply about, the harder part of this is what is the slope? It needs to have the right slope. And so again, that's the harder part of this. So let's start talking about the slope of the tangent line and how we might find this. Okay, we are going to use the fact that we know what a secant slope is in order to help us develop how we figure out what a tangent slope of a line is. So just so we're clear, let us kind of just, we've got two parabolas here. It's any kind of curve, it doesn't matter. We're going to want to talk about secant slopes. Maybe let's get a little bit of shorthand notation for these things and also tangent slope. So for secant slope, let's use the symbol m for slope. But we also have tangent slope, so we're going to want to distinguish between these. So let's put like an SEC for secant down in like the subscript. This is going to mean slope of the secant line. For the tangent slopes, or for the tangent lines, for their slopes, let's do the same thing. Let's use m, and then let's use tan in the subscript just to talk about the tangent line slope. Okay, so on the graph on the left, if we wanted to find the slope of the secant line, for example, could be any 2 points, but let's just choose 2 points here. Of course, that's going to look like this. Right, this is a secant line. If we wanted to find the slope of this line, all we would need to do is find change in y over change in x. So let's just label what these points are. Like maybe we'll call this point here x1, comma y1. And let's call this point over here x2, comma y2. Right, and as we know, the slope of this line, or m secant, slope of the secant line, that's just rise over run, or change in y over change in x. Or maybe more specifically, y2 minus y1 over x2 minus x1. We know this already, right? This is our notion of slope of a line. If we wanted to find the tangent lines and their slopes, well, we only have 1 point, right? As we said before. So if we wanted to find the tangent line here, I mean, we could sketch it in. Maybe again, it looks something like this. But again, like the slope is going to be 0 over 0 if we try to use our old formula, right? If we do change in y over change in x with 1 point, we're going to get 0 up top and 0 in the bottom. So the only thing we could say here, the best thing we could say about this tangent line is that it's positive. That we know. It goes up from left to right. If we draw a tangent line somewhere else, like maybe over here, that's going to have negative slope, right? Because that's going to look something like this. Again, we only have 1 point, so the slope is going to be 0 over 0. So here we have negative slope. We could also have 0 slope somewhere. So, if we want to find the tangent line here, that would look like a horizontal line. And here the tangent line slope is 0. So in all of these cases, the slope of the tangent line, if you try to use the old formula, we're going to get 0 over 0. So using the secant line formula or the slope formula, right, we know that this is going to give 0 over 0. But as we can see, the tangent line slope could be positive, it could be negative, or it could be 0. So obviously this 0 over 0 could actually turn out to be anything once we develop a better method to find this compared to our previous formula for slope that unfortunately needs 2 points. Okay, so using the slope formula gives 0 over 0, but this could turn out to be positive, to be negative, or even 0. This kind of might remind you, hopefully, of something that we've seen with limits. Right? When we find a limit and with direct substitution, we get 0 over 0, we try to remove that whole, and we can actually end up getting any value that could be, it could be positive, negative number, it could be 0 after we eliminate that whole. So keep that in mind. Limits are going to come into play here. We'll see in just a few minutes. The idea with this, right, we don't have a formula for this just yet. We will very soon. So let's actually look at a specific example and estimate the slope of the tangent line in various methods, in various ways. So how do we actually calculate the slope of a tangent line? Again, this is our focus for this section. How do we actually do this? So let's look at the function f of x equals x squared, the next simplest function aside from a line. And let's estimate the slope of the tangent line at the point 3, 9. We're going to do this in 3 different ways: graphically, numerically, and then also algebraically. However, when we develop the actual best way of doing this, we're not going to use the graphical method or the numerical method. We'll have a better way that will basically be the algebraic method. Okay, so this is just for the sake of understanding what's going on. We'll look at the graphical and numerical way. The algebraic way is pretty much the way that we're going to be using from here on out after this example. So just to note that here, this is how we'll do this. Always. This is how we'll always do this. Something like that, I don't know, after this example. So take a second to sketch a pretty sizable, like a nice graph of the function y equals x squared. We're just focusing at the point 3, 9. So I'm only using the positive x-axis here and the positive y-axis. Right, so we find the y values. We could plot some points: 0, 0, right? 1, 1, because 1 squared is 1, 2 squared is 4, so there's that point. 3 squared is 9, so there's that point, and then 4 squared is 16, and so there's that point. Now sketch a tangent line to the point that we're interested in. Right, that's right here at 3, 9. Do your best to extend it a little bit. Maybe like enough to get a second point here. I know mine looks like, maybe this is the best. I know it looks like it kind of touches the curve a lot, but it's just because my, lines have a thickness, but we understand that it just touches that one point there, right here at 3, 9. So I hope yours looks something like this. If we extend to find another point, I mean, I don't have any grids here or anything, but I do see that another point I could probably read off kind of easily right here is on the x-axis, the x-intercept. This is about 1.5, 0. So now I've got 2 points on this line that I want to find the equation of. So I could just do that now using the old way. It's going to be change in y, we're changing x. Okay, so that's 9 minus 0 over 3 minus 1.5. All right, that's 9 over 1.5, and that comes out to be 6. Okay, so here's an estimation of the slope of the tangent line to this curve at 3, 9. Obviously, this method isn't great because you might have gotten a different slope. It depends how you draw this. If the function were more complicated, it might be even worse. We'll see that this is actually a pretty good approximation, but we have a pretty simple graph. So the next best thing that we might consider doing is a numerical way. So actually, plugging and chugging some numbers in and seeing what's going to happen here. Okay, so the numerical method, the idea behind this, again, is to take points closer and closer. Is to take points closer and closer and closer to the point that we're interested in, which is 3, 9, and then find the slope of the line that it goes through those 2 points. Because we're just kind of using what we know here, right? Slope goes through 2 points. So we're just going to take, a point that's really close, pretty close to 3, 9, and then find the secant slopes between the point that we're choosing and then 3, 9. So here's our function, right? It's f of x equals x squared. So we know that the one point that we are looking at is 3, 9. So the second point that we might choose, a point that's pretty close to 3, 9, might have an x value of like, I don't know, 3.5. Like that's pretty close. So if you look up on our graph here from the previous method, right, 3.5 on the x-axis would be here. And so the point that we're looking at on the curve is going to be right here on the x squared curve. And what we're doing is we're going to find the slope of the secant line that goes between these 2 points now, using the notion of slope that we're used to. So I'm not going to draw it here because it'll get really kind of cluttered, but it's going to look like this. Again, it's really hard to tell that that's what's happening here. But we do need the y value. So to find the y value on the function y equals x squared at 3.5, we're going to just plug in 3.5 for x into x squared. Right, we're just plugging this into here. That'll give us the y value. So when you square 3.5, you get 12.25. Okay, so let's find the slope. So this is going to be a secant slope. Again, it's just change in y over change in x. Okay, so we've got 12.25 minus 9, that's our change in y. Our change in x will be 3.5 minus 3. Okay, when you subtract these, you're going to get, up top, you'll get 3.25. Down bottom, we'll get 0.5. And when you divide these, you should get 6.5. Okay, so that's a good estimate for our slope of the tangent line. But we can get a point that's closer. Instead of 3.5, maybe we'll choose 3.1, right? That's a point on the curve, so 3.1 might be like here. On the black curve, on the x squared curve, that's even closer to the point that we're interested in than 3.5 was. So let's try that. Okay, to find the y value of that point, again, we're just going to take 3.1 and we're going to square it because that's the function that this point lives on. When you square 3.1, you will get 9.61. Again, we're going to find the secant slope. And again, that is change in y over change in x. This time we'll have 9.61 minus 9 over 3.1 minus 3. Okay, so that's 0.61 over 0.1, and that comes out to be 6.1. So this is an even better approximation of our true secant slope. But we can get a better approximation by taking a point that's even closer. Instead of 3.1, maybe we'll choose 3.01. Right, that's pretty super close. 3.01 and 3 are pretty close together. To find the y value of this point, again, we're just going to square 3.01 and plug it into the function. And when we do that, we'll get 9.0601. Okay, so when we find the secant slope between those 2 points, again, it'll just be change in y over change in x. We'll subtract 9.0601 minus 9, and then subtract 3.01 minus 3. Okay, so the change in y here will be 0.0601, and the change in x will be 0.01. And when we divide these, we'll get 6.01. Now notice that the change in y's up top in the numerators, these are getting really small. That makes sense because our points are getting closer together, right? The change in x's, these are getting really small too. That also should make sense because again, the points that we're choosing, the 1 point that we're choosing is moving closer along the curve to the point 3,9. Let's just do one more. How about 3.001? That might be a pretty nice close point to the point 3,9. When you plug in 3.001 into f of x equals x squared, you're going to get 9.006001. All right, let's find the secant slope between these 2 points. That'll be 9.006001 minus 9 over 3.001 minus 3. All right, so that's 0.006001, an even smaller change in y, over 0.001, an even smaller change in x. Right, these tops are approaching 0, the bottoms are also approaching 0. And when we divide these, we're going to get 6.001. I hope this method kind of reminds you of something. Right, this is really like a limit. What we are doing is we're letting our second point approach 3,9, but it will never actually hit that point 3,9 because if it does, our slope is automatically gone. It's just 0 over 0. So what we can do is do this notion of this would be like a numerical approach to finding the limit of the secant slopes, which would approximate the tangent line slopes. Okay, so what these points, these slopes are doing here, these are of course approaching 6. Okay, so the slopes, the secant slopes, approach a tangent line slope of 6 as the point gets closer to the point of interest. So as the second point approaches 3,9. And so this method would kind of suggest that the tangent line slope at the point 3,9 would be 6. Now sometimes, again, this is a very simple function. This is, the slope here, it's easy to see that the slopes that we have are approaching 6. But of course, there are many more complicated functions. What if this was approaching like the square root of 2 or something? How would we be able to see that and get an exact answer? So this method is pretty tedious and also just a little like not great. So a better way that we could do this is algebraically. So here is how this might be set up. We're going to generalize the second point from the previous method as instead of like choosing a numerical value for it, like 3.1, 3.01, 3.001, what we'll do is say, okay, well, what we're doing is we've got 3 plus a little bit. So 3 plus like 0.5, 3 plus 0.1, 3 plus 0.01, 3 plus 0.001. So that little difference we're going to call delta x. That's going to be the x coordinate of the point that we're going to bring closer to the point 3,9. And then the y coordinate for that point will be, well, f of that point, right? So f of 3 plus delta x. Right, it's always like just x comma y or x comma f of x. That's how you find the y values. So all we're doing here is to find the y value at this x value. We're just plugging that in for the input into the function. So in other words, like, this would be 3.1 squared. Really, it's f of 3.1. Or 3.01 squared, right? F of 3.01. So that's what this is representing over here. So what we'll do is now build the secant line slope through this second point and the point that we are interested in, which again is 3, 9. So the secant slope between this point that we've generalized and our original point is still going to be the change in y over change in x. So the change in y will just be f of 3 plus delta x minus f of 3. It's just the y values at the 2 points that we have. And then divided by the change in x, which will be the change in the x values. So 3 plus delta x and then minus 3. Then all we're going to do with this is make the delta x shrink and get really small. That'll bring the points closer together, or bring the second point closer to the 3, 9. Right, 3, 9 isn't moving. It's just this second point that we're bringing down closer to the point that we want to find the tangent line at. So the mathematical tool in order to do that, this is where the limit's going to come in. So what we're going to do is take the limit as delta x approaches 0. So our points will get infinitely close together when we find this limit. So this will actually, once we have all of this set up, the secant line slope between these 2 points, then actually making that second point get infinitely close to the original point of 3, 9, this will then become equal to the tangent line slope. This is really cool because this is bringing together 2 ideas that we've talked about already. What we have over here is basically a difference quotient. It looks a little bit different, but it's like f of x plus h minus f of x all over x plus h. That's essentially what this is. And then also, we're finding the limit of a difference quotient. And this is going to give us the slope, the exact slope of the tangent line. So let's take some time to actually calculate what this is for our particular function. Now notice when you try to actually, when we're finding limits, we try direct substitution first. If you put in a 0 for delta x here and here, you're going to get f of 3 minus f of 3, which is 0, and then 3 minus 3 in the bottom, which is 0. That makes sense because that would mean that the 2 points are exactly the same. But we're not going to do that yet, right? We need to remove the whole in order to figure out what this limit is. So let's see. Let's get this f of part away. So f of 3 plus delta x. Remember, our function here is f of x equals x squared. So if we're going to plug in 3 plus delta x into the function, we're plugging all of this in to x here. So we're going to square in parentheses 3 plus delta x. Now f of 3, that's 3 squared, right? That's 9. That's just the y value of the point. And then, of course, 3 plus delta x minus 3, that's just delta x. That's the change in x. Now, we still haven't canceled out the 0 over 0, so we have to kind of expand all of this. We have to FOIL this out and then see what happens. So when we FOIL out the 3 plus delta x, we're going to get 9 plus 3 delta x plus 3 delta x, so that's 6 delta x, and then plus delta x squared. If we're not sure where that's coming from, take a sec to actually work out what this would be. right? This is going to be 3 plus delta x times 3 plus delta x. So you just might need to distribute everything out, right? We have the first, then the outer, then the inner, then the last, and you'll end up with this here. And then minus 9, that is 3 squared. Okay, and then this is, now we're like off in our limit calculating land, so we just need to decide what's going to happen here with the canceling and stuff. So it looks like we have 9 minus 9, so those add up to 0. Okay, then up top, what we have left is 6 delta x plus delta x squared all over delta x. Remember, in order to cancel out this delta x, what we need in order to do that is factor out the delta x from the numerator. So essential step here, we need to be able to cancel out a delta x with every piece up top. And you can see that more clearly if you are able to factor it out of every term in the numerator. And I think we can. Right, we'll end up with delta x times parentheses 6 plus delta x. Now here we can cancel out the delta x's. They will divide to give us 1. That's the point where we removed the 0 over 0. So now it is safe for us to plug in the delta x equals 0 now, right? So here we've got direct substitution, 6 plus 0. Of course, that's just 6. I hope not surprisingly, right? We should get the same thing no matter what method we're trying to use in general with mathematics. But this is basically like proof that the actual value of the tangent line slope is exactly 6. We're not saying, oh, it looks like it's 6, or the numbers suggest that it's going to be 6. This is saying that it actually is 6. So this is, in fact, 100% the slope of that tangent line there. So like I said, this method, the algebraic method, is how we're going to be finding slopes of tangent lines and what we'll call the derivative in just a minute. But we don't want to have to do this for every single point, right? This is just focusing in on the point 3, 9. So we're going to want to generalize this to any x value or any point. And when we do that, we get a new function. Okay, so we're going to generalize this idea for any point x comma y and for any function f of x. When we do that, we get something called the derivative of a function. Our derivative result, or what we get when we actually do this generalization, is going to be a formula with x's in it. In other words, another function. So the derivative is another function, but this time the derivative, the information it tells you isn't the height of the function or the y values. The outputs give the slopes of the tangent line. It's a formula for the slopes of the tangent line to the original graph y equals f of x at any x value. Really cool. This derivative function, the outputs of it are related to the original, but what they give you is the slopes of the tangent line at any x value that you could want. So it is calculated by finding a limit. I'm going to build the limit by also showing you a picture of what's going on. So let's just sketch a generic function here. Let's get some axes. Here's my y-axis, here's my x-axis. And I don't know, maybe here's the function that we'll call y equals f of x. So this is the original one that we start with. What we're looking for is the slope of the tangent line at any point that we want. So let's just say, okay, maybe we're looking right here. This is where we want to find the tangent line at. We want to generalize this to not be 3 comma 9, but to be any x coordinate, xy coordinate. So let's call this x. Then the y value there, that's going to be f of x. It's whatever it is when you plug in that x value into the function, which could be anything. We're very generalized here. All right, then what we're going to do is pick another point. Let's call this one, I don't know where it, how about it lives somewhere over here. This is going to be x plus a little bit, x plus delta x. Or if you like h, you can use that too. If you don't like the delta x, it is a little clunky. Some people use h in place of delta x, like we did in the difference quotient. You can do that. Then that means that the y value here is going to be f of x plus delta x. Now what we want is the slope of the tangent line here. We're looking for this line slope. But what we do in order to find that is find a secant line between 2 points. We find the slope between those 2 points on that secant line. So what will that be? So here it'll be change in y. So that height there, that's just the upper y value minus the lower y value. So it's just this distance, right? So it's this upper y value minus the lower y value. The change in x, this distance here, if we go from x to x plus delta x, that distance is just delta x. So that's why we were using delta x, because it represents the change in the x coordinates. Right, so then the slope of the secant line is going to be f of x plus delta x minus f of x, that's the change in y, over the change in x. But this is a secant slope, a slope between 2 points. We want the tangent line slope. So what we do is we bring this green point all along the curve and let it approach the pink point, the one that we're finding the tangent line at. How do we do this? Well, we let the limit as delta x approaches 0. That's how we do that. We let the green point move along the curve and see what's happening to the slope. So we need to also include the limit as delta x approaches 0 here. And then what this blue line is going to do, what this secant line is going to do, is just, if we have a point here, right, we'll have a different secant line with a different slope. But as you get closer and closer and closer and closer, right, the 2 points will be so close together that the secant line will resemble or be really close to a tangent line. And that is what a derivative is, the slope of that line. So we're going to be talking about derivatives every single day that I see you or that you watch a video from here on out. We do have a few different ways of notating the derivative. So as I mentioned before, there were a couple guys who developed or discovered or created, however you want to think about it, calculus around the same time. They both developed different ways of notating the derivative. So I actually don't know what name, like who came up with the name derivative. I've never thought about that before. So anyway, one of those ways is slope of the tangent line. We're not going to use this, but it is important to know that the derivative, one of the interpretations, is the slope of the tangent line. Okay, so I'll put that in parentheses. The most common way to notate the derivative is to, it comes from the function f of x. So to notate the derivative that's related to the original function, we put an apostrophe. And we say this as f prime of x. That's the derivative of f of x, f prime of x. We could also say y prime. You know, if we have like y equals, we might use y prime instead. Another way that you could notate the derivative is instead of delta y over delta x, really the deltas are getting infinitely tiny. They're approaching 0. They never get there, but they get infinitely close to 0. So it's like infinity, but in the opposite direction, kind of like infinitely small, as opposed to infinitely large. These are called infinitesimals. And instead of delta y over delta x, when we're talking about infinitely small changes, we use a d. So we use dy over dx. And that's just how you'd say that, dy dx, or dy over dx. And the last way that we'll see is related to dy dx. We can write d dx to mean take the derivative of what comes next. So d dx of f of x is just kind of a way to notate, hey, we're going to take the derivative of f of x in like the next step here. So d dx of f of x means what follows after this is the derivative of what's inside of the brackets. So let us use this definition to actually calculate the derivative of f of x equals x squared, right? That's the function that we have been focusing on for the last while. So let's find the derivative of f of x is equal to x squared. So I'm going to start by, we only have one tool, it's our formula, right? So f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. This is just the formula for finding the derivative. Now we need to figure out what it is for our specific function, for x squared. So let's see, this part here in the pink, let's figure out what that is. So this is just plugging in x plus delta x in for x. So this is really similar to plugging in the 3 plus delta x into the x squared like we did when we were looking at this at 3, 9 before. Right, what this function does is just squares everything that's in the input. The whole thing that's in the input here is x plus delta x. This whole thing here inside the parentheses, that's the input, this whole blob. So this whole blob is going to be squared. Okay, then f of x, I mean, that's just x squared, right? That's nothing that's hard to find, right? F of x, that's just the function itself. And then the delta x, that's just delta x, that just stays in there. So let's put in what we've got here. We've got the limit as delta x approaches 0. We've got x plus delta x squared. That's the f of x plus delta x. Then we've got minus x squared. And then that's all over delta x. Now remember, our goal is going to be to eventually cancel out the delta x so that we can figure out what, what this limit's going to be. So I think we should probably expand this out. Let's expand that by foiling. So if you need to do a little bit of work on the side, by all means. So let's see, we've got x plus delta x times x plus delta x. Okay, so the first gives us x squared, right? X times x. Then we'll get plus x times delta x. Now you want to think of that delta x as a single piece together, like a single symbol, even though it's made up of a delta and an x. In other words, this isn't like delta x squared or something. You never just want to think of the delta as being by itself. So x delta x is an unlike term from the x squared. Then what did we just do? First and outer, so we've got the inner, so that's another x delta x, and then plus delta x squared. That's kind of why I'm putting the delta x in parentheses here once it shows up, because then we don't confuse the square being on the x only. Okay, so that's why that is in parentheses. Then we can combine the x delta x's. That's just 2x delta x. So that's what we have in the pink stuff here, right? That's what that becomes, is all of this. So let's put that in. Okay, x squared plus 2x times delta x plus parentheses delta x squared, and then we still have minus x squared. And then we still have over delta x. Okay, again, just to show you, right, that's just that stuff expanded. That's just staying as x squared. Of course, delta x is just staying as it is for now. Okay, here's the fun part where we can cancel stuff out. Let us see what we have. X squareds, I think. Right, those will add up to 0. So then what we have left, I think that's everything. Yeah, that's everything. Is a 2x times delta x, and then plus a delta x squared. Okay, remember our goal is to cancel out the delta x. So we have to do that by factoring it out from the numerator, just like in our other example. Again, if you like to use h's instead, you might practice that and see that you like that better. That's fine. You can use an h instead of delta x. I like the delta x because it gives us a sense of the geometric interpretation of this stuff. So just a good reminder for me that that's what is actually happening. When we factor out a delta x from the top, we get 2x plus delta x left in the bottom. Okay, here we can finally divide those delta x's or remove the whole, the 0 over 0. What we're left with is 2x plus delta x. Now that we canceled out the 0 over 0, now what we can do is direct substitute in. Now be careful what we're plugging in here, or what we're substituting in for, right? It's delta x approaches 0, not x. So, right, x is a general placeholder for any point that we want to find the tangent line at. Here, we're just letting delta x approach 0. So this is going to end up being 2x and then plus 0, which is just 2x. And so that's the derivative. Okay, so for f of x equals x squared, what we found is that f prime of x, the derivative, is equal to 2x. Right, so these go together. The derivative of x squared is 2x. Now, how do we reconcile this with the fact that we found a 6 before? Well, this is a general formula for any point that we want to find the tangent line slope at. So let's just remember that. This is a formula. This 2x is a formula for the slope of the tangent line to f of x at any x value. Okay, we don't have to do it over and over again for different points. We just have a formula here. So for f of x, for x equals 3, we have f prime of 3, which would be 2 times 3, which is 6. And that matches what we found before, right? The slope of the tangent line, 2x squared at the point 3, 9 is equal to 6. I hope this is as exciting for you as it is for me. We'll be talking about this a lot more in the next couple videos, and again for the rest of the semester. But I do want to share with you just this little tweet that Steven Strogatz, who is a mathematician, he has a lot of interesting books that he has written to kind of bring interesting and really complex mathematical ideas to people who are considered themselves as like non-math people. So anyway, he put this online where he calculated his first derivative with his daughter, and this is kind of how I feel every time that I go through calculating a derivative for the first time with a group of students. So anyway, in the next video, what we will do is more practice with this, and we will also find some slopes to curves at different points and also find some equations of tangent lines. So tune into that, and I'll see you then.